Okay, we're taking a look at the 2015 calculus free response question number 6. Okay, consider the curve given by the equation y cubed minus xy equals 2. It can be shown that the derivative dy dx is equal to y over 3y squared minus x. For part A, write an equation for the line tangent to the curve at the point negative 1, 1. So what information do you need to write the equation of a tangent line? Remember, for a tangent line, we need a point and a slope. So for part A, we already have the point. They gave us the point, so we need to figure out the slope. So to find the slope, what we're going to do is we're going to take that point and plug it into the derivative. Okay, so negative 1, 1 into y, so 1 over 3 times y squared minus negative 1. Okay. So let's see here. On the top, I just get 1, and the bottom 3 minus negative 1 would be 4. So my slope is 1/4. So the equation of the tangent line, y minus 1, y minus the y coordinate equals the slope times x minus the x coordinate. Okay? Or you could say plus 1. So y minus 1 equals 1/4 times x plus 1. Okay? Okay, there's your equation of the tangent line. For part B, it says find the coordinates of all points on the curve at which the line tangent to the graph, to the curve, at that point is vertical. So when would I have a vertical tangent line? Okay, so if I have a vertical tangent line, then my derivative would need to be undefined. And when is a fraction undefined? A fraction is undefined when the denominator equals 0. So 3y squared minus x is equal to 0. What we're going to do is we're going to solve this. I think the easiest variable to solve this for would be the x. So 3y squared is equal to x. So there's this relationship here, but I need to find all the points, find the coordinates of all points on the curve. So what we're going to do is we're going to take that 3y squared equals x and use it as part of a substitution in my original curve. Okay, so y cubed minus x, so the x is going to change into 3y squared times y equals 2. All right, so let's keep solving this. Y cubed would stay the same, minus 3y cubed equals 2. All right, 1y cubed minus 3y cubed would be negative 2y cubed equals 2. Y cubed equals negative 1, so y is equal to negative 1. So now that I have y, I need to find x. A couple different ways of doing that. You could plug it back into the original, or we could just plug it into the substitution, this relationship here, right? So 3 times negative 1 squared is equal to x. So 3 equals x. So the answer here, the point, is 3 comma negative 1. Okay? So that's where my derivative would be undefined. Okay? Part C, evaluate the second derivative at the point on the curve where x equals negative 1 and 1, and y equals 1. So evaluate the second derivative. So what that means is we need to find the second derivative. So for part C, dy dx, I'm going to go ahead and rewrite my original function. So y over 3y squared minus x. I need to find a second derivative. So when I take the derivative of this, because this is a fraction and I have variables in both the top and the bottom, I want to use the quotient rule. Okay. So the second derivative would be low times the derivative of the high, dy dx, minus the high times the derivative of the low, so 6y dy over dx, right, minus 1. Now remember, when I take the derivative of y with respect to x, we need to add in a dy dx. And then when I take the derivative of the denominator here, we take the derivative of the term 3y squared, so that's where the 6y comes from. And then I need to take the derivative of y with respect to x. So that's why we include the dy dx there. And then the derivative of minus x would be minus 1. All over low, so which would be the low squared. Okay? And we've got to simplify this. We've got to plug in the point 1 comma, or x equals -1 and y is equal to 1. Now we can kind of do some of this stuff off to the side. You've got some choices here. Dy dx is equal to all of this, so you could put that in for each dy dx in the problem. That's going to get really complicated really quick because you're going to have fractions on top of fractions, which we'd like to avoid if we can. Okay, so instead what we can do is we can just evaluate that dy dx term off to the side. Okay, and I think if we look back to part A, we already did that, right? We already evaluated the derivative at -1, 1. And we found that the derivative at -1, 1 is 1/4. So anywhere where there's a dy dx in the problem, when I evaluate this, I can just put in 1/4. So I'm going to have 3 times the y value is 1 minus -1. Dy dx is 1/4 minus the y value of 1. 6 times 1, 1/4 times 1/4 minus 1. All over 3 times 1 minus -1 squared. Have an extra parenthesis there. Okay, so let's start simplifying this. 3 times 1 squared minus -1 would just be 4. So 4 times 1/4 minus, let's see here, I've got 6 times 1/4, which is 3/2 minus 1, all over 3 times 1 plus 1 squared, which would be 16. So 1 minus 1/2 over 16 equals 1/2 over 16. Flip the second and multiply, so 1/2 times 1/16 would be 1 over 32. Okay, final answer. Okay, so let's talk about points. In part A, you would get 1 point for finding the slope, 1 point for the equation of the tangent line. For part B, you would get 1 point for setting it equal to 0, 1 point for writing your equation in terms of one variable, and then 1 point for your coordinates. Okay. In part C, you're going to get 2 points total for finding the correct derivative. Okay, it's kind of an all or nothing there on that one. When you substitute in your dy dx, now whether you put in the number, 1/4, or you put in the fraction and then simplify it all the way, you're going to get your 1 point, and then 1 point for a final answer of 1/32. Okay? Not too bad. A little bit of a throwback on this one. Okay. Let me know if you have any questions.